Okay, so the basic idea then is that we have some embedding space, and our space-time is some sort of a curved space in this embedding space. As far as we know, our space-time is four-dimensional, although the string theorists tell us that maybe it's 10-dimensional. Whatever it is, I'm just going to, for the purposes of this course, I'm basically going to be talking about four-dimensional space-time. But whether it's 4 or 10, we put it inside a larger Euclidean space that we can embed it in. And remember last time, scalars were things that are the same in a coordinate system. Remember that the vectors dxi prime are, of course, partial xi prime partial xj dxj. Here I'm using Einstein's summation convention, which is basically that if we have one upper index and one lower index, this index is lower because it's below the fraction line. Then we sum over it from 0 to 3 or whatever it is. This summation convention is used more generally and is more useful than just in the case of special and general relativity. Whenever you have anything with indices, you almost always are summing over the indices when the indices are repeated.
And we have contravariant for superscripts.
These guys are,
covariant
this
for
is
subscripts.
contravariant. So these are the guys, I guess, that Reagan was supporting back there in the 80s, contras. Now we also have ordinary derivatives transformed this way, di prime, which is to say partial xi is, let me just do this, partial xi, partial x, oh, this is x prime I, and this then would be partial xj, partial xj, or equivalently it is partial xj, partial x prime I, partial j. I like this notation because it just saves us so much writing. So this is covariant. And this is just a chain rule calculus, and it defines what we mean by these covariant and contravariant vectors. Now, the idea is basically that we have points P on some manifold. These points are physical, and we can describe these points by coordinates P of x or coordinates P of x prime. And in fact, the 2 points are the same because they're just different descriptions of the same physical point. Okay. Now, where we touch physics is in a funny sort of place. Suppose you have 2 points that are close to each other. Then the distance between them is, well, the 2 points are physical, and the distance between them is physical, but there's a nuance here. What is the correct distance between them that is actually physical? And the funny thing is that it's not what one would ordinarily think. You'd ordinarily, if you're making furniture in 3 dimensions, then it's the ordinary distance. But in reality, it's it's a distance associated with special and general relativity. And so I'm going to depart a little bit from the notes, so you want to watch me for typos. If you see a mistake, say something. So first of all, I want to define, let's consider the partial derivative of the point with respect to some coordinates, so effectively BIP. Well, this is clearly then a covariant vector, and we can call it EI. In fact, we can call it EI of x if we're using the x coordinates. Now, what we want is we want to say, what is the change in P? Well, it's going to be EI dxi. So that's the distance, that's the change in P as you change your coordinates a little bit. Now, let's consider this. Let's consider dp dot dp. Well, this is going to be EI dot dj dxi dxj. Now,
you get a metric tensor like that, right?
Right. You're ahead of the game, but so let me sneak up on this. So the point here is if you have dx dot dp, well, we can call this gij. And we expect this to be invariant, this to be both physical and to be invariant under changes of coordinates. And now, let's consider what this gij you have. You see, these EIs are actually vectors in this big embedding space. And so this dot product here of EI dot j, which is gij, is equal to an EIA EJB eta AB, where eta AB is the flat space metric of the embedding space. So eta AB is minus 1, 1, 1, 1, 1, 1, 1, however many there are there. I think for the purposes of 4 dimensions in this course, we can say, well, 8 is enough. If we include singularities, maybe you need more. But anyway, let's just take 8. So that's what the physics tells us, namely that there is something that's invariant here, no matter what the coordinates are that we choose. It's this structure that's going to be invariant. And notice that it's not, you can't just say, well, let's just consider the spatial distance squared between 2 points, like this point and that point. Well, that spatial distance will look different to somebody moving with a velocity relative to the velocity of this room. So that basically is the idea of the metric tensor and so forth. All right, let me see what else I want to say here, because I'm sort of skipping through things here, which we have to do if we're going to cover GR and some other stuff at this rate of 1 lecture a week. All right, I should maybe say a little bit about for relativity. All I'm going to say is that we have the inhomogeneous Maxwell equations look like this. Okay, so mu0 is I forget what the technical name for it is. It's the magnetic constant. Duh. So that's the magnetic constant. This is the current, and this is the divergence. This is basically the F mu, which is E and B, and it's antisymmetric at K and I. So these are what are called the inhomogeneous Maxwell equations. There are two other vector Maxwell equations, which these are the homogeneous Maxwell equations, and these are written as epsilon L ijk di f jk equals 0. Now, I'm writing these in the form of special relativity. And in the case of general relativity, there's a small change here. This turns into a covariant derivative. The other one remains basically the same. Okay, and we imagine having things that have more than one contravariant or covariant index, and they transform, each index transforms contravariantly or covariantly. If you have the rank of a tensor is the number of indices, basically. And if you have two tensors of the same kind, you can add them together. So, okay. All right. Let me just say a few words about differential forms, because there's something about them that's really quite. There's one part that's quite nice and quite easy to understand, and then there are other parts that are interesting but much harder to understand. I'm going to skip those because the notation gets really complicated.
Wedge products and exterior algebras?
Yeah. So I'm going to do the simple part, and I'm going to skip the Hodge star.
The Hodge dual?
The Hodge star is in the book, but I don't think it's all that important. Okay. Differential forms. Now, here's the interesting thing. We have let's see, how do I want to say it? We can take it, suppose we have a covariant vector, and we sum it into the differentials, the contravariant differentials. Well, this is going to be invariant. In fact, anything with one upper and one lower index, if you sum over it, is invariant. And let me just show you why. Because if you do put in primes here, then first of all, how does the covariant vector behave? Well, it's partial xj, partial x prime I, that's this index. And this then will be aj. And this guy is partial of x prime I, partial x k dx k. Okay. Now, despite the fact that my left arm is down, I've got this right without a typo. Just by the chain rule, the partial xj, partial x prime I times partial x prime I, partial xk. So this is just partial xj, partial xk times aj dxk. Of course, this is just the Kronecker delta. This is one when they're the same, 0 when they are. And notice, it's 1 period, not 1 or minus 1, depending on it. So whether the j and k are 0 or time indices or space indices, no problem. And so this is delta j aj dxk, and this is then just aj dxj. So in other words, this thing here is invariant. And so it makes sense then, in fact, we could even say that it's physical. In any event, it's invariant, and it's called a one form. And the person who invented these forms was Élie Cartan, who lived until 1951, actually, and was the son of a blacksmith. And the fact that he rose so high in mathematics is a tribute to the French social system that actually believes in education. Bernie Sanders. And so this thing is what we will call A, and as I said, it's a one form. And another thing that Cartan introduced apart from the idea of forms, or one forms, two forms, we'll get to them in a minute, he talked about something called a wedge product. And this wedge product is, in particular, it's anti-symmetric. And it's basically, in a sense, it's defined as the oriented area spanned by these two dx differentials, if they happen to be vectors. And what you can see, actually, is that if you change coordinates, then du wedge dv, I'll skip all the algebra. It's partial of u with respect to x, partial of u with respect to y, partial vx, partial vy, all of that dx wedge dy. And so this is useful when you change coordinates.
Is that a Jacobian matrix?
Yeah, this is the Jacobian. So what are these other forms? Well, you can form something like this. 1/2 hi k dxi wedge dxk. Well, you can see this is going to be invariant because it's has one. This is a second rank 2 covariant tensor, and it's dotted into this wedge product, and so it's invariant under general coordinate transformations. And this thing is called then a two form. And in general, a p form is the same thing, that you have a p index, you have p of these differentials. Notice that h is automatically anti-symmetric because any symmetric part here just cancels, because this guy is anti-symmetric. Okay, so these ideas are important and simple, and that's the kind of thing I like to stress, is important and simple as opposed to complicated and unimportant. The next idea is the exterior derivative. Exterior derivative d. And this is something that's, if you apply it to a function, you can think of a function as a zero form. Well, this is partial of f, partial xi, dxi. Well, this thing is a covariant derivative, so this is a one form. So this takes a zero form to a one form. But it also takes a one form to a two form and so forth. And let me see if I can find the nicest version of that. Yeah, okay, for some reason I don't, yeah, here's a nice version of it, okay. So let's take, let's suppose that this particular one form is in fact the one form of the electromagnetic field. And I've run out of blackboard space, so let me go over here. So let's apply let's see, we have some light problem here, and I'm a little worried that this could screw up the lighting of the camera. The camera adjusts to that. So let's do this. Let's just say, let's apply this exterior derivative to the one form of the electromagnetic potential, say. So this then will be partial xj of AI dxj wedge dxi. Well, this thing is anti-symmetric, so it's only the anti-symmetric part of this that contributes. So we can say this is 1/2 partial AI partial xj minus partial aj partial xi dxi wedge dxj. And, well, what's this? This is f mu nu. This is fij. So this is 1/2 fij dxi wedge dxj. So what we've seen is that this exterior derivative is pretty useful. It turns the electromagnetic potentials, or the one form of the electromagnetic field, into the two form of a Maxwell tensor, the E and B's. And so this is really quite cute. And now suppose, what happens if we do this again? Suppose we just do df. Well, this would then be 1/2 partial xk fij dxk dxj. By the way, when you do this, let me just flip back to here. This exterior derivative, when it hits the zero form, you then sum over all the coordinates. So it would be 0 to 4 in the normal case. It could be more or fewer. And when it hits this, the one form, it sums over j from 0 to 3. So now we've got this thing here that is, it's actually going to be 0. And the reason it's 0 is that it's, how shall I, let me see if I get this straight. I'm having a little, okay, let me back up one to say what this is. This is actually d by dx k dx, whoops, hold on. This thing here of AI dxj dxk wedge dxi wedge dxj. Okay, so that's what it is. But now, this thing is symmetric in k and j, but it's anti-symmetric in k and j over here. The way to see that is you can bring the dxj forward, that's an overall minus sign, and then you've got dxk wedge dxj, that's anti-symmetric in k and j. And so this is equal to 0. And so what we have then is an invariant equation, df equals 0. Well, this turns out to be the two homogeneous Maxwell equations. That is to say, this is the same thing as this over here. And to see that this is two equations, notice that we're summing over Ij and k, but there's an L left over, which can be 0 to 3. So those are four equations. The four equations are del dot b equals 0. That equation doesn't really have a name as far as I know. I jokingly thought of calling it, there's this guy, experimentalist at Stanford, who thought he had discovered magnetic monopoles about 20 years ago. He was doing an experiment looking for them, and I don't know if it was random noise or statistical fluctuation, or one of the graduate students played prank on it, I don't know. But the signal went away. Anyway, that's one equation. The other equation is curl of E plus B dot equals 0. And that equation I did name here is it's Faraday's law. So this is Faraday, and I forget the monopole guy, so I can't tell you. I can't even make a decent joke of it. Okay, so that's let's see, do I want to say anything more about differential forms? Well, it's in general true that dd anything, so I'll just call it Z, equals 0. So the exterior derivative applied twice to any form, a 0 form, a p form, whatever, 0. Let's just think about this. Suppose we have dq equals 0. And what we say here is that q is closed. And then we would say, suppose we can say that q is equal to d of something else, dp. Then we would say q is exact. Now, what is true is that any form that's exact is closed, because if q is equal to dp, then dq is automatically 0 because dd is 0. What Poincaré showed was that you can go the other way. If you have a form that's closed, then it's locally exact. In other words, you can draw a sphere around the point you're talking about, and if in that sphere the Q is closed, then you can show that it's actually exact in that sphere, and that's called Poincaré's lemma. Poincaré undoubtedly had thousands of lemmas. Why we refer to that as Poincaré's lemma is something that it's always puzzled me. But okay. And an example of this is, suppose you have, let us say we have an electric field. Well, if the electric field is static, or let us say that if we're talking about a static electric and magnetic, actually if the magnetic field is static, then by Faraday's equation, if B dot is 0, the curl of E vanishes. So let's say the curl of E vanishes. If the curl of E is 0, then what you can do is you can, and what can we say, how can we describe that? What we can do is we can say that dE, E being a one form, so this is D of di dxi, but now I goes from 1 to 3 here. And so this is partial di, partial xj, dxj wedge dxi. So this is saying that the antisymmetric combination here of d is 0. That's just what we say curl of e is 0. If the curl of e is 0, then it doesn't matter whether you integrate e like this or you integrate e that way, you get the same thing. And in fact, that's the work done on a charge, moving it in a static electric field, a static kinetic field. And so the way you do that then is you can then define v of x as the integral from some reference point x0 up to x of e of x prime dot dx prime. And ordinarily this would be path dependent. You could always do, even if the curl of e didn't vanish, you could define this, but it would depend on the path. If the curl of e vanishes, it's path independent, and then you have this. Then what you can say is that e is dv, or rather, yeah, e is minus dv, minus partial e partial xi dxi, like that. And of course, then you can say dE is 0 because it's d squared on v, and that's dE presents that. Okay. All right, so all that is fine.
So
I think that's all I'm going to say about forms.
E is exact, then?
E, yeah, E is, if you can write E as dV, it's exact. And the fact, no, what the hell is closed here?
Well, even if
Well, E is closed.
E is closed and exact.
Yeah, that's right. E is exact, but it's also closed because dE is 0. But and dE is 0 whenever B dot vanishes. Okay. All right. So these. So let me just say one thing then about one of the advantages of the viewpoint in Einstein's viewpoint in general relativity is that the action of the theory is invariant of general coordinate transformations, and as a consequence, all the equations are invariant of general coordinate transformations. And that means that you don't need to say what coordinate system you're using. You just have to write the equations in their general form, and then it doesn't matter who looks at them, they're still correct. And that's basically the way things really have to be. And so basically, if you write things, Einstein's point of view, well, one of the things he said was if you write things as tensor equations, where everything in the equation is a tensor, well then it'll look the same in any coordinates, because when you make a coordinate transformation, you just get all those crazy partial derivatives. And then when you're finished, you just have the equation with everything with primes written over it, or the equation without the primes. By the way, let me tell you what in particular and in fact, the homogeneous Maxwell equations, of course, dA equals 0. These are the two homogeneous equations. They're true in general relativity. And that's because these are tensor or invariant equations. The inhomogeneous equations need a little bit of work, and the actual form they have is this. biggest difference between this and the thing I wrote down that's true in special relativity is I interchanged I and K, which of course makes no difference. The change brought about by general relativity is you stick in the square root of the determinant of the metric. So G is this 4x4 matrix that I basically defined on the first board. That is to say G on J is EI dot EJ, or equivalently it's partial of the point with respect to xi, dotted into partial of the point with respect to xj. And the dot is that these points are in the embedding space, and so when you take this derivative, you have in general more than, in other words, this thing is partial PA, partial xi, partial PB, partial xj, eta AB, where you sum over A and B from, let us say, 0 to 8 or 9. Okay. Well, not 9. 0 to 7 or 8. And the physics here is that although we're talking about the embedding space being 8-dimensional, say, Euclidean space, when we talk about the dot product of these vectors, which are called tangent vectors, by the way, we use this Minkowski metric, the flat space Minkowski metric of the embedding space. And then we get something that's, well, it's a second-rank tensor, but we get that dp squared is invariant, and that then is Gij dx dxj. All right, so there's something called the Quotient Theorem, and I guess I'll prove it for the smallest piece. So suppose we have bi, now let's e prime a prime is equal to, okay, so suppose for all contravariant vectors A, this B thing satisfies this rule where bi prime is bi in the other coordinate system. So we make a change of coordinate systems. This thing, which should be invariant, is equal to this, where we've changed the contravariant vector A correctly, and we say that we've changed B correctly, but we don't really know how B changes. And the point is that B has to be a covariant vector. And the way we show that is that this thing is certainly B prime I partial x prime I partial x j, just because A is a contravariant vector. And now we set this equal to that by hypothesis, and so we have B prime I partial x prime I partial x j minus bj aj equals 0. So I combine these two together. And now what we do is we multiply both sides by, actually I don't know why I did this. this was just useless, because all I need to do is multiply both sides of this by the correct. Oh, no, I did need to do this. This is true for arbitrary contravariant vectors A. Consequently, we can promote it to a vector equation, and then we have as a vector equation B prime I partial x prime I partial xj is equal to j. Now we multiply that by partial xj partial x prime k, and in fact, to avoid hell, let me get an eraser. So what I'm going to do here is I'm going to rewrite this as, and I'm going to multiply it by partial xj partial xk, partial xj, partial xk, and there's a prime here somewhere. Prime is down there. Okay. Now this thing summed over j just gives us partial x prime I, partial x prime k. That is b prime I delta ik equals ej partial xj partial x prime k. But this, of course, is b prime k. But this thing is just a transformation law for a covariant vector. So the upshot is, if you have a vector such that for every contravariant vector, its dot product with it is invariant, then that thing must have been a covariant vector. This is called the Quotient Theorem, and it's much more general than that, but in its more general form, the proof is conceptually the same as this. And all right. Okay. So let's get back to this metric that we defined in a particular way as the dot product in the embedding space of the tangent vectors. And see how it transforms. Well, G prime ij will be partial of p with respect to x prime phi partial p partial x prime j. That's one way of thinking of it, but what I actually wanted to do was to say, well, this is x prime I dot of x prime j. Actually, it's the same thing. In other words, this partial x, I should have not done, I should have just stated this. This is partial p partial x k partial xk partial x prime I, and then the other one is partial p partial xl partial xl partial x prime j, and we still have this thing is dotted into that, and so this is gkl times partial xk partial x prime I partial xl partial x prime j. So that's how that works. So you see that the metric tensor automatically transforms as a second rank covariant tensor, just from the way it's defined. And So, but all of these ideas that apply to four manifolds in this higher dimensional embedding space also apply to making furniture in 3 dimensions. And for example, we can consider a point on a sphere. And then we consider E theta, for example, is partial of P, which is now a 3-vector partial theta. And this is R, theta hat. And then E phi, partial P, this is R sine theta phi hat. And then we get a metric tensor then. I'm going to just skip a couple of equations. It's R squared 0, 0, R squared sine squared theta. And this is just, this is E theta dot E theta, the dot product being in 3 dimensions, E phi dot E phi, and then E theta dot E phi is 0. The contravariant metric tensor, well, what is that? That is, well, first of all, what is the inverse of the metric tensor? G upper ij is simply defined such that, so the second rank contravariant metric tensor is just defined to be the inverse of the metric tensor. And moreover, this is an equation that, of course, it's a tensor equation, so it's invariant. So it's also true that G prime I J, G prime J K is also equal to 0, because delta prime I K is the same as delta I K. And so what one can show then is that, in fact, what we can do is we can apply the quotient theorem. Okay? Let's apply the quotient theorem. Here we have, well, I shouldn't say we can apply the quotient theorem, but actually we maybe can't quite, because we don't have we don't have arbitrary ones. Anyway, it turns out, if you do a little bit of arithmetic, what you can find out that this transforms the right way, namely it's partial x prime I, partial x v, partial x prime L, partial x w, g, beta. So in other words, it really is a second rank contravariant tensor. All right, I think we can go maybe a couple of more minutes because we started a few minutes late. Well, if we just refer to the book, there's some things, orthogonal coordinates, Euclidean end space, polar coordinates, cylindrical coordinates. Maybe I should say something about, well, that's 2 space. Let me skip to 3 space. If we have spherical coordinates in 3 space, well, then what do we have? G ij looks like this. So I'm going to skip a lot of algebra here. It's in the book. R squared. So it's basically what we learned here, just that we now think of this as, we're thinking of it as, this is interesting, it's kind of this way. You see, if we speak about the sphere intrinsically as a 2 surface, then this is the 2 metric for the surface of the sphere. On the other hand, if you think about a sphere as embedded in free space, then this is the metric of the sphere in free space. And so that basically is that. Maybe I'll just say a word about a gradient and then we can mix it up. So the gradient basically would be defined this way. The gradient plotted into dp is df. And so this thing would be dot e I dxi, and this is gradient of f dot that equals partial f partial xi dxi. And so what we've got is that the gradient must be something such that dotted into the vectors ei, you get partial f partial xi. And so in other words, okay, I forgot to mention something here, namely that we have all these vectors. We can define the vector ei such that ei dot bj is delta ij. These are called the dual vectors. And notice that the thing is 1 here, if I and j is. And so what we say here then is that grad f must be e upper I times partial f partial xi. Because you see then dotted into e lower I, you get this equation. And this again is this is an invariant quantity because this is a contravariant vector, and this is a covariant vector. Okay, I think we can stop here and